not, I want to talk about an idea that I think is really neat. Again, the work of Anat Levin and Bob Fergus, Fredo Durand, and Bill Freeman. So here's what it does in a nutshell. You take an image, and from this image, using a lot of number crunching, you can compute in one shot a depth map and then the appearance itself. Because if you zoom in a little, the original image that was acquired, it's not very crisp, and this is so what you get after reconstruction is both an improved image and the depth map itself. In terms of our famous image, this is what it does. So first let me show you the device. I have a picture somewhere. There. So the lens was opened by hand. The pattern, which is not random, but was carefully optimized, has been cut out from a piece of cardboard, probably with a scalpel and lots of patience, and was fixed in the lens, inside the lens with some just tape. The whole thing was reassembled, and in the talk it says very nicely, the lens was $79, the cardboard was $1, the tape was $1, and you get depth information, which is priceless. So how does it work? Let's again look at the image of a single lens. I had argued before that this line here corresponds to this point, and that line there corresponds to that point of our integration over the light field, and the intermediate rays correspond to intermediate points. Now imagine, what if we block certain rays? Let's say we block the second ray and we block the fifth ray. So from this integration box, I would eliminate this part and I would eliminate that part. And this is achieved by putting, in your aperture, piece of cardboard with a few holes. Do I have an image? Sorry for the scrolling there. This explains the picture shown in our mantra here. Yeah? So we have, by blocking some of the rays through this piece of cardboard, we have eliminated part of these integration regions in our ordinary lens camera. And also note again that it is that one lens, or sorry, one sensing element acquires the average over all of these. Okay, so these are not three different values, but I've just measured one value, which is the sum over all of the things that I see in these boxes here. So here is on the left-hand side what an ordinary aperture looks like, and on the right-hand side, after you've put your glue and stuff in, what such a coated aperture looks like. And on the bottom are the circles of confusion. And the ordinary circle of confusion can be seen as in this image by Mr. Rohrbach. So we have some point sources that are out of focus, and we here observe the image of those point sources, or their circle of confusion, or in this case it was an aperture with 5 half planes that block the light outside. Apparently these are called pentaflares. Yeah, so we see, in a way, we now look at the aperture of the lens system used by this photographer. So this is what a normal flare would look like. See, this corresponds to this pentagon in here. And on the right-hand side is the blur pattern from this complicated aperture. And what it looks like, so again, the aperture is the one shown, well, just here. And what exactly this blur pattern looks like is distance dependent. So these pictures are again from the Levin paper. Here you see for various distances what the blur pattern looks like in the center of the image. And then actually there are higher, there are other artifacts, which means that if you look at the very left part of your image or the very right part of your image, actually the blur patterns look a little bit different. The camera is not rotation invariant. So we want to recover both the image and the depth. So how can we do it with this funny measuring of parts of the light field? Let's start with the assumption that if the depth were known, then we would have the following optimization problem. I would have a blur operator. So everything here is in matrix and vector notation, where O is my observed image, X is my estimate of the true image, C is the distance-dependent blur, which can be measured. So the distance-dependent blur is known, and of course the observed image is known. But unfortunately, so this is a distance image, which is not known. But for the time being, I assume that the depth is being known. Okay, so if D is known, we want to solve this only for X. And altogether for D known, I could say this is a supervised deblurring. Which is a much studied problem. Now such an inversion, or solving such an inverse problem that can, you always have noise in your image, so this would probably give you some funny artifacts. So it's a good idea to regularize this. And the way the authors regularized it here was to take the finite differences in the horizontal direction of the image, of the estimated image, and take this to some power, and the finite differences in the vertical direction of the image, the estimated image, and take that to some power. And then we still need to trade off somehow this regularization versus the data term. So those are finite difference operators. Oh, just between a pixel and its adjacent pixel. Okay, so F, H, x at the, it's a bit difficult to write down because all of these things are vectorized. But what it does is it takes the pixel value minus the adjacent pixel value. That's all. This penalty here, it's a bit funny. It's not an LP norm. If I wanted this to be an LP norm, I would have to take 1 over the 0.8 square root of these terms also, or of the sum of these terms. That's not happening here. But in any case, this is something that penalizes gradients, and it prefers having a large gradient occasionally over having small gradients everywhere. So altogether, this is I could say that this is a smoothness prior favoring sparse gradients. So it likes images that are piecewise constant. And it's quite typical to use such a smoothness prior in supervised deblurring, so I can extend my brace over the entire formula here. And these operations here, when I say take the norm or take it to the power of 0.8, all of this is meant as element-wise operations. Now this problem here is non-convex with these powers of 0.8. And you can only solve this to a local optimum. And the authors here do it using iteratively reweighted least squares. Now, in actual fact, however, the depth is unknown, which I just assumed for the time being that it was known. So their suggestion here is to do the following, to simply try this out for multiple depths. So this is a heuristic recipe. You solve the above problem multiple times. For different constant values of your depth d. And you then, over a sliding window, estimate the reconstruction errors. So you look at how far you look at the magnitude of this first term and average this over a small window. You do that for all possible values of your depth d. And then you locally pick your depth that gives you the smallest reconstruction error. You then get a very noisy depth estimate. It's done, so the D is picked patchwise. So you have, I think, overlapping patches. And then you finally smooth your depth map D using an MRF, Markov random field, where the authors have tried out a contrast-sensitive Potts term for the regularization part. So really what you would like to optimize is the following. You would like to optimize over both your unknown image X and the depth map D, and you would allow the depth to, vary continuously. I'm abbreviating the regularization term from further up as R of x, which is smoothness prior that enforces sparse gradients. And now we have, in addition, a smoothness prior on the depth map, which is of a different form. So the first one uses sparse gradients, and the second one uses contrast sensitive Potts prior. So whenever the depth changes from one pixel to the next, you pay some penalty, but the penalty you pay is smaller if there's also a strong gradient in the image that you estimate locally. So, in a way, this depends on D and X. And this is a difficult coupled optimization problem, and the authors don't write it down directly in this form, but rather use this heuristic where, as I said, you first try out different depth values, locally estimate how good they are, and then use that as input for an MRF. So the reconstruction error is just this thing here. So O is measured, C is for a given D is a linear operator, X is your estimate, and you just see, how close to zero this is locally. And the idea is that if you pick the wrong depth, so if you use a blur kernel corresponding to the wrong depth, this will give you strong ringing artifacts. And these ringing so if you look at it, besides each strong gradient, you see ripples. And if you now subtract this rippled image from your original image, you get a large residual, which is a reconstruction error. So I think this is a paper with a high coolness factor. So it's really a minor tweak to the hardware, and then much use of computers. It's a fairly hard optimization problem. Apart from the computation, the no free lunch theorem here tells us that you lose light. So in these cardboard parts of your aperture, this blocks the light, so you need longer exposure times, or you get a somewhat noisier image. But still, I thought it was a really neat idea. References. There are plenty, but two good websites are the one from Todor Georgiev, who used to be with Adobe and now is with Qualcomm, and Mark Lavoie, whose group has over the last 20 years made consistent, important contribution to this field. You can now buy two different systems. So there's Lytro, which has which was founded by Andrew Ng, not Andrew Ng, Ren Ng, who used to be this PhD student of Mark Lavoie. And they've taken a fairly long time from the invention to market. So the camera came out, I think, a year or so ago, but the papers are from the early 2000s. And then here's a company that has one of the fastest times to market that I've seen, because I happened to be there in 2008 when Christian Perwas was talking to Georgiev and learning about these things for the first time. And then I think 2 years later there was the company and the product. And but it's a friendly competition. I think they more or less cross-reference each other and so on. And these are the systems that you can currently buy for a reasonable price. And the first one I think is more geared towards end consumers. And let me see if I can. Do I have a? Can I type here somehow? Whereas the second one I think is mostly geared towards industrial quality inspection. So they have a fun interactive gallery where you can click on your favorite picture and then ask it, for example, when I now click here, I ask it to refocus here, and it does. Okay, so you have here a user community and I think an app that allows you to easily, upload your own if you've bought one of these cameras. And Raytrix, I think, yeah, as I said, looks mostly at industrial quality control. So these things have made it to the real world. You can buy them. If you are from the area here, there is the group of Bastian Goldlücke, who is interested in light fields and who devotes his entire recent work to the area. So if you're interested in playing with this sort of data and making projects, he's a good address. He also has acquired some light fields and so on, which he makes available on his homepage.